My guest today is Professor Emil Martinec, who's Professor of Physics at the Enrico Fermi Institute and the College of the University of Chicago. His research focuses on string theory and particle physics. Welcome, Emil.
Hi, glad to be here.
Yeah, so thanks for doing this on a weekend. So you are one of the early pioneers of string theory. String theory, as I believe, started late 60s, early 70s. But you and your team at Princeton in the mid 80s had a new version of string theory when string theory sort of came back in force after a while. So I know that one of the issues we have in the standard model is that we haven't gotten gravity into the room yet. And string theory appears to have some promises in that direction. Could you give a sort of a brief history of string theory and where we are?
Sure. String theory originally arose out of the particle physics of the 1960s as an attempt to understand the plethora of strongly interacting particles that people were seeing in particle accelerators. And they were trying to understand, so like every time you would turn on a new accelerator that had a little bit higher energy than the previous generation, you would find yet more new particles that sort of cropped up as you slammed these subatomic particles together. And so as a way of trying to organize this data, people came up with the idea of string theory, that somehow there was some microscopic extended object whose different vibrational states would account for the different strongly interacting particles that were being seen as intermediate states in scattering experiments at accelerators. Now, that turned out not to be quite the right idea. That we now know that the fundamental theory of the strong interactions is something called quantum chromodynamics, and that the string idea was a kind of a phenomenological approximation that worked well in a particular range of energies. And so string theory, so as soon as that was realized, people were exploring the standard model, more and more deeply during the 1970s, and string theory kind of fell into a backwater during that decade. But one important piece of progress came in the middle of that decade, where if you really treated the string as some kind of fundamental object and asked, what's the spectrum of string excitations, that surprisingly it contained a massless spin-2 particle as part of the spectrum. And the massless spin-2 particle is the hallmark of gravitational physics. The gravitons that we detect at LIGO are such massless spin-2 particles. And so all of us, a gradual evolution of thinking came about then. Maybe this string theory is not so great as a phenomenological description of strong interaction. Maybe it's something more fundamental. And in that if it has gravity in it as a low energy approximation, then maybe we should sort of set our sights higher and ask whether string theory is good as a theory of unification of all the fundamental forces. And so that idea percolated along for another decade until this revolution that you were mentioning earlier in 1984, where we really started putting the pieces together of string theory as a theory of unification of all the fundamental forces. And there was a burst of activity then in the mid to late 80s along those lines, in which I participated in my postgraduate and early professorial career. And at that time, we were exploring the idea of, okay, how could string theory be a theory of unification? What would the needed ingredients be? And so what you would need is an explanation of all the other forces in the standard model, quantum chromodynamics that I mentioned earlier is the theory of strong interactions, electromagnetism that we see and use every day to see each other and make wonderful computing devices, and so on, and something called the weak interactions, which is related to radioactivity and other processes of that sort. And so those are the sort of three basic forces that we know of in addition to gravity. And while string theory doesn't uniquely generate a sort of a necessary outcome, those forces can be accommodated in a description of, in a unified description where those are also different resonances of the string. You try to explain the matter particles we see, like quarks and electrons and neutrinos and other matter particles, as yet other sorts of excitations of this basic string-like object. And so at that level, the theory is sort of a success. You say, okay, everything I know about in nature can be incorporated in string theory. Initially there was some hope that construction would be relatively unique, that there wouldn't be that choices, and be, on to constructing a unified theory there. But as people learn more about string theory, they learned that actually the constructions aren't so unique. And the way physics works is there's sort of two, and constructing any physical theory, you have to ask two questions. What are the basic, laws that are governing the phenomenon that you're describing? Like Newton's laws of motion, or Maxwell's equations of electromagnetism, or Einstein's equation of general, the dynamic situation. And then there's some question, okay, of the equation are you studying? So Einstein's equations have many solutions. They have, for instance, Big Bang cosmology and black hole physics and all sorts of different solutions. So you have to ask the question, which solution describes our world? And that's where string theory is sort of, the seeming uniqueness of string theory all of a sudden encounters a roadblock in that we don't know exactly which solution we're describing. And so, so a lot of the developments, since that period have been trying to focus on, the sort of how to build the ingredients of the standard model and what of properties of string theory look more like the real world that we see around us and which ones don't. So that's sort of like one track that the theory has gone on.
Yeah.
And then another track has gone on trying to understand better. Sorry.
No, so I'm just going to say, so from my own understanding, Emil, so yep. First we thought molecules were fundamental, then we thought atoms were fundamental, then we found quarks inside neutrons and protons, and the standard model was sort of filling up, as you say, inelegantly all these particles that we find in high energy physics. And the motivation here is to say, can we go one level further into something more fundamental than quarks, right? Yes. That was really the motivation. And it's mathematically elegant, but I guess the downside is it's really difficult to prove that it's in fact true. We don't have a lot of predictions or testable hypotheses. Yes. Is that true?
That's true. So at the moment, it's a vast extrapolation of what we've learned about particle physics, and to claim that you really have something fundamental, and that this process of peeling away the layers of structure has an end, where this is the deepest level of structure and there's nothing deeper than that. It takes there's a certain amount of hubris in making a claim of that sort, especially when, if you ask, okay, what is this deepest layer of structure that string theory is postulating? Well, as you said, as we've gotten more and more powerful microscopes to look at the world, we saw more and more, layers of structure from molecules to atoms to atomic nuclei to nuclear structure to quarks inside of protons. Why doesn't it just keep going? And there are hints. There's no experimental proof because, well, what are our more powerful microscopes? Well, once you get below the subatomic level, the sizes of atoms, your microscopes are particle accelerators. And the way that works is basically Heisenberg's uncertainty principle, that the more energy and momentum you have in colliding a particle, and Heisenberg tells you that the scale of the momentum is sort of inversely related to a resolution scale, given by his uncertainty principle, that the uncertainty in momentum times the uncertainty in position is his Planck's constant h bar. And so if you want to probe some small resolution delta x, you need a large p. And so the idea, since the dawn of the atomic the quantum more particle deeper and deeper levels. And so right now our most powerful accelerator is the Large Hadron Collider in CERN that has an energy of about 1,000 times the mass of the proton. And so we can see sort of to the scale of, well, that much deeper than the size of a proton, we can see some of the structure underlying the weak interactions, which is at a scale of 1/4 of a TeV, roughly. But we can't go much further. We don't have the ability to go much further than that. Basically, already the Large Hadron Collider is tens of kilometers in size. And that's starting to reach the limits of what's humanly achievable. And you can ask, okay, what's the scale now that string theory is postulating? Well, we'll have to hedge a little bit here because it depends on what exactly we're looking at in terms of a solution to string theory. But the solutions of string theory that people typically work with as being approximations of the world that we see have a level of structure which of the deepest structure, which is, well, the Planck scale. And what's the Planck scale? It's not 1,000 times the mass of the proton. It's 10 to the 19 times the mass of the proton. In other words, 10 with 19 zeros. So we have sort of 19 orders. We've gotten to 1,000 times the mass of the proton. There's sort of 16 more orders of magnitude before you get to the fundamental scales set by string theory. And so you could ask, okay, so there's several questions you could ask then. One question you could ask is, okay, well, are there more and more layers of structure in between, a TeV and the Planck scale? We just, are skimming the surface of yet more layers to be uncovered? Or is there what particle physicists in the 70s used to call the desert, that sort of there's this scale of around 1,000 GeV, and then there kind of isn't much until you get to some kind of scale of unification, which might be close to the Planck scale, maybe a few orders of magnitude below, but then sort of there would be this, not so much going on in the region in between. And there are reasons, sort of hints that might be the case just by the precision experiments we've done in the standard model. But we don't know for sure, experimentally.
So when you say layers there, Emil, I don't know much about this. So from 10 to the power 3 to 10 to the power 19, when there are layers in between those, are we talking about different types of strings? Or what do those layers represent?
So there are a number of scales that we imagine could be going on in between. One scale that we might uncover might have to do with neutrino physics, indicate that there might be something going on around 10 to the 14 GeV. If there's one scale that's sort of hinted at by the standard model is that there is a weak evolution of the strength of the different interactions in the standard model. A sort of logarithmic variation with scale that comes about because there is, well, let me not go into the details unless you're interested. But basically, there's a slow variation of the coupling. So the strong interactions are strong at the scales that we measure them, like the scale of the proton. That's what binds quarks and keeps quarks from getting out in isolation outside of protons. And then there's, as I was saying, the scale of the weak interactions around 250 GeV, and then there's the scale of the strength of electromagnetism. All of those different interactions, if you study how they evolve slowly with energy scale, you find that they all kind of converge to close to the same strength at a scale of about 10 to the 16 to 10 to the 17 GeV. What physicists were thinking might be some kind of scale of further unification of the gauge forces into some deeper symmetry. So in the 1970s, as soon as people figured out the standard model, they started thinking about, okay, what's the next layer deeper? And one of the hints they had was this sort of meeting of what was called the running of the couplings. That the couplings sort of diverged in their strengths at low energies, but at high energies, they all converged to some sort of uniform value. And that might be some hint of some deeper structure. So there are these hints that they're deeper structures, but they all seem to be within, that there's this sort of like big gap between the 10 to the 3 that we currently see and scales like 10 to the 14, 10 to the 16, 10 to the 19.
But we're still talking about strong, weak, and electromagnetic forces. We don't really have much idea about gravity.
We don't have much idea about the scale at which gravity has the same strength as these other forces that we know about is around that scale. So in a sense, the sort of the ultimate scale of unification is, I think we presume, the Planck scale, that there aren't any scales more fundamental than that.
Yeah, I sometimes feel.
But there can be, but for instance, string theory. So if you could ask, okay, if the way string theory came about as a theory of unification was, as I was saying earlier, the idea that all the different particles and forces that we see at low energies are different manifestations of the string and its vibrations and its interactions. So you could ask, so all of those low energy particles that you see in the standard model in this proposal are different kind of low energy, what I would call unexcited strings, different kinds of unexcited strings. And our sort of intuition about this is sort of copied from the way string theory originally arose in the strong interactions, where the different resonances that people were seeing in particle accelerators were thought to be different excited states of the string. And people used to plot, okay, what's the mass of the particle as a function of the spin? And what they were seeing were very uniform, what were called Regge trajectories, where you make those plots and you would see that there were regularly spaced particles every time you increase the spin of the particle by 1 unit, that you would find another particle which had sort of 2 times, 3 times, 4 times the mass of some basic number. And the basic number was the string tension. So it's very simple to see. It's like you start spinning a string, okay, the centrifugal force tries to stretch it. Okay, and so it costs you some energy to stretch the string, but energy is mass according to Einstein, E equals mc squared. And so the more and more complicated and more you excite the string and try to make it rotate and so on, the heavier you make it because it has to stretch. And so there's some scale in string theory, which is the scale of this stretching energy called the string tension. And we don't know. So one of the scales that we kind of don't have any information about at the moment, but we presume is, again, somewhere up close to the Planck scale, is the scale of the string tension. And where we would start seeing excited vibrational states of the string, and not just these unexcited states, which are the quarks and the gluons and photons and so on.
Yeah, so I guess the beauty is that everything is sort of naturally quantized
Yes.
in the process. So everything sort of mathematically fits. I sometimes feel, Emil, that God is playing a nice trick on us. You find something and there is more complex behind it, and this goes on like that. So in some ways, string theory is a nice way to say, we're going to stop here. We're not going to prove anything. Here is nice, beautiful mathematics that appears to fit everything, and we can throw it back at her, back at God, and say we are done. We're not going to prove anything anymore. And there are two implications. She might turn us off, or she might give us a different problem.
Yeah, string theory seems to be very good at hiding itself, right? I mean, the fundamental scale where we expect to see all the stringy structure in terms of these excited resonances, the Planck scale, and so on. Those are all way up at some energy scale where we'll never build a particle accelerator that has that much energy to see any of that structure. And that's kind of one of the reasons why in the last 25 years or so, people have turned their attention to black hole physics. I don't know if this is a convenient time to go there, but the basic idea is that gravity is attractive. So if you pile enough, mass in one place, it collapses to make a black hole. And in Einstein's theory of gravity, a black hole is a kind of a runaway collapse. That is, the more and more compact you make things, the stronger the gravitational forces are, because things are far apart, gravitational forces are weak, but they get close together, gravitational forces are strong. And the formation of a black hole is a place where, according to Einstein's theory, this process, this gravitational attraction just causes things to start accelerating towards one another. And that acceleration just runs away. And in Einstein's theory, that runaway leads to the formation of what's called a gravitational singularity, which is, presumably what happens in the core of the black hole, according to Einstein's theory. But if you're thinking in a particle physicist terms, this is like a dream come true, that there's this process, it's just like, nature sets it up and you let it go and it runs. And all of a sudden, particles get accelerated to arbitrarily high energy as they approach each other. So why don't we just, watch one of these things form and, instrument the outside of it, detect the decay products, and, we learn something about quantum gravity. Well, that would be nice if nature was kind, but unfortunately, nature cloaks the singularity by an event horizon that we can't see what's going. Sort of erects a black box and says you can't look inside this black box, unless you dive into the singularity yourself.
Right.
So black holes are like the ultimate particle accelerator. It's just that we don't understand them well enough to first of all, we can't access them, the core of the black hole experimentally, and theoretically we're still having a hard time coming to grips with what is exactly going on in these very rarefied regimes of compacting mass and gravitational strong forces.
Yeah, so I want to go into black hole physics. Before we go there, Emil, I wanted to, the way I understand it, string theory requires 10 total dimensions, 9 spatial dimensions and 1 time dimension. And then M theory requires an additional space dimension. So is this sort of a testable thing? I mean, if we can prove some sort of dimension that we typically don't think about, 3 + 1 exists in some way, then that is really the important proof, right, for string theory?
Yeah. So indeed, the mathematical consistency of string theory requires there to be these additional 6 or 7 spatial dimensions, which we obviously don't see. There are 2 things to say about that. One is that, you could ask how. I said strings, that the particles that we see come out in string theory as some kind of unexcited string states. What did I mean by unexcited string states? Well, the way that mass comes about in string theory is you have to ask yourself kind of, how does the string arrange itself in space? If you like in any modern theory, there's a spectrum of energies, and that you get by solving some equations, like the Schrodinger equation of quantum mechanics, and so the low energy particles, the particles whose masses we see, like the electron, quarks, and so on, those are extremely light compared to the Planck scale. So there should be some reason why they're so much lighter than the Planck scale. And this is where some of the mathematics of string theory starts coming in, that the way you can protect such particles from getting some mass from some stringy effects at some high energy scale is to have them be guaranteed to be light by some kind of topological reasoning. So topology is a branch of mathematics that guarantees that no matter how you wiggle the interactions or the structure, there's the topological aspects are things that are independent of those wigglings. And so if you want a light particle, you would like it to be light for some reason like that no matter how you change the interactions at high energy, the fact that the electron is as light as it is guaranteed to you. And so one of the sort of uses of these extra dimensions in string theory is that if you postulate that they're of some really tiny size, but have some topology, you can use that topology of the extra dimensions to predict the spectrum of particles in the standard model. Let me state that a little bit more carefully. If you knew the right compactification, its topology. So this gets back to this issue of you have equations and then you have solutions. Okay, the solutions of the equations that we're interested in to make contact with our real world have only 3 big dimensions, the 3 dimensions of space that we see. The other 6 or 7 are then postulated to be of some tiny size, so small that we can't. Again, our particle accelerators are microscopes. They can only sort of resolve space down to some distance scale inversely proportional to their energy. Yeah. And so if these extra dimensions are smaller than the scale set by a TeV, the scale that the LHC can probe, then we have no way of sort of resolving the presence of those extra dimensions. They're just too tiny to excite anything that measures them. And so all you would see are these sort of like topological residues of the extra dimensions. And the topological residues of the extra dimensions are the light particles that we see in the standard model. So, but one of the reasons we were sort of optimistic in the mid-'80s was that not many of these compactifications of geometry were known. And so maybe, we'd be lucky and there were only a few, and we could, we could just, look and see which one matches the data and we'd be done. That was sort of the mid-'80s, hubris, I was calling it. Well, of course, as soon as you turn a mathematician and ask them, okay, well, how many solutions are of the, Einstein's equations, with 6 dimensions and your favorite topology are there? you turn them loose on this problem and they say, oh, yeah, well, there's this way of constructing them, that way of constructing them. And, now the number of known constructions of such compactifications is, 10 to the whatever, 10 to the 500, or there's a number that's commonly quoted, but, i.e., an enormous number. And so it almost becomes hopeless to find amongst all of those different solutions of string theory which one exactly describes nature. The status of this project of unifying the forces is kind of stuck on this issue of which solution of the equations is the right one that describes the world that we see.
But
and so, yeah.
Even if you, so these dimensions are so small, they're not experimentally resolvable to the energy levels we can ever accomplish, right? So it wouldn't, we won't be able to experimentally validate in any way, right?
It's extremely unlikely. It's extremely unlikely.
Extremely unlikely.
I mean, the sort of running, the sort of conventional wisdom is that the scale of the size of these extra dimensions, this what's called a compactification, these extra dimensions are, if you were small enough to walk around in them, you started walking around and you'd go, 100 Planck lengths and you'd come back to where you started. So that's kind of the idea of them being small.
Yeah.
And if they're that small, then for the same reasons, you'll never make fundamental strings with a string tension of 10 to the 14th GeV. You'll never make something that's probing these extra dimensions. So when one says that string theory is a theory of extra dimensions, you have to ask sort of operationally, what do you mean by extra dimensions? Suppose the extra dimensions were the Planck scale in size. What do I mean by a dimension that I can't walk around in? That if I take 2 steps, I come back to where I started? It sort of becomes a meaningless question. So I think the way I would phrase it is string theory can accommodate any dimension from the number that we see on up to 10 or 11. And operationally, the issue of is there a dimension there or not is a question of what is the structure of the spectrum of the theory, the spectrum of energies that, quantized energies that the theory has in it, in this regime of energy scales up around the Planck scale. And, do we see because like if we look at, particles in the everyday world, the spectrum of energies has to do with the different momenta that we can give them going in different directions. And quantum mechanics tells us that if we try to confine something to a given size, the spectrum of energies becomes discrete and inversely proportional to the size. So the reason why we can't sort of probe these extra dimensions is that the cost in energy, there's a big gap between the energies we can make and the energy cost of the lightest excitation that sees the structure of the extra dimensions. So if the extra dimensions are, 15, 16, 17 orders of magnitude in energy smaller than we can make, then we can never make any excitations with any conventional technology that would see this structure.
So in some sense, that extra dimensions are fundamental in themselves. It's a bit like looking for the strings. We won't be able to see the strings, nor would we ever be able to solve the extra dimensions, right?
Yeah, so I think that the sort of state of the art at the moment is trying to ask what structures, one of the attractions of string theory is it tends to convert questions about particle physics into questions about geometry, right? So when I say the spectrum of low energy particles is tied to these topological characteristics, these sort of like immutable characteristics of the extra dimensions, and what particular geometry they have.
Yeah.
You've all of a sudden turned a question about, how many different species of quarks are there, and how many different species of electrons and neutrinos, and how many gauge particles are there in the Standard Model. You convert questions like that into questions about what is the geometry of the extra dimensions. So one of the attractions of string theory is this sort of deep interplay between particle physics and mathematics. And you can say, okay, if I'm a geometer talking about the geometry of six-dimensional, compact spaces, and I wanted to engineer the Standard Model, so you say, okay, what are the geometrical ingredients that I need to piece together in this compact space that make precisely the things that we see in particle physics? So you like turn the question on its head from one of, how do we verify string theory is like, how do we use the ingredients of string theory to build what we know?
Yeah. The problem obviously is, 100,000 years of Homo sapien evolution gave a set of intuitions, and that is going to be very countercultural in many ways to string theory.
Yes.
And so, in some sense, like you say, you start in mathematics and you try to explain your experience in some way. You have to almost assume that mathematics is true. Because proving mathematics from what we conventionally hold as intuition, we probably cannot get anywhere with that, I would think.
Yeah, well, I think humans are good at developing new intuitions. So, one of the, great revolutions in physics was the quantum revolution of the 1920s. And I think part of the problem we face 100 years later is that the quantum world is at the atomic scale, but we're, 10 to the 10 times bigger than that. So our intuitions are built on things that are very classical. And so part of the reason I think we struggle with quantum mechanics is that indeed our brains our forebrains are not very well adapted to thinking quantum mechanically. And so, we sort of try to work around that. And one of the reasons we develop mathematics is to give us the language in which to couch new intuitions. There was a flurry of activity after quantum mechanics was discovered, developing the new mathematics, operator algebras, linear algebra, Hilbert spaces, all the structure of quantum mechanics there were pieces of it that were in place, because the people that developed the Schrodinger equation and so on, or Heisenberg's matrix theory, there were bits and pieces of that linear algebra that they could, cobble together to make the first theories of quantum mechanics. But then once you've got the theory, you say, okay, what's the natural mathematical language in which to express the ideas that we're seeing? And so you develop new mathematics to help you, develop your intuition. And so I think string theory is engaged on a long project of that sort. There is, if you like, some new mathematics that we began to discover in the late 1960s and then reapplied in the mid 70s to quantum gravity. And we're still trying to, figure out, what is the, full extent of the set of, new mathematics that we need in order to figure out what this theory is. And we only have bits and pieces of that.
Yeah, I wonder, Emil, in some sense, you need to shed your Homo sapien intuition baggage. So perhaps students of physics today, or people starting off today, may not have a lot of classical views of the world. And they might be in a better position to really think about it. I think the classical brain is sort of we have that baggage to get over, right? When we think about new stuff.
We have that baggage, and we also have our preconceptions to overcome. So one reason I think that a lot of breakthroughs in physics are done by young people is that they don't know what they can't do.
Right.
They have no preconceptions about the way the world should work, and so there's also that aspect as well. You have sort of a blank slate, if you like,
That's
to develop new intuitions and new theories.
Yeah, so I want to go into black hole physics. It's sort of related topic. So you mentioned that, so we have this entity out there. We sort of know how it might have formed. So it's sort of a nice experimental. I mean, we cannot see anything, but it's a nice laboratory to at least start asking questions around some of these things, right? So one thing I was wondering about, I mean, I don't know if this is the right way to think about it. Is the black hole a singularity in space or a singularity in time, or both?
So it's both, but predominantly a singularity in time. And in fact, one of the reasons people are interested in studying the singularity of the black hole is that we have another singularity in time that we know about, which is the Big Bang. And so it's hoped that if we can learn enough about quantum gravity by studying black holes, that some of that, new intuition will carry over into developing better ideas about cosmology. And we can talk about that a little bit later if you like, but maybe just to summarize for those people who don't have the background, one of the hallmarks of Einstein's theory of gravity is that if you have a massive object and you ask, what are the trajectories of light rays as they pass by that massive object? Well, according to Einstein's theory, they get bent a little bit. So in a way, a mass acts like a lens that focuses light rays. And in fact, that one of the earliest verifications of Einstein's theory was studying the apparent positions of stars during a solar eclipse in 1919. That they took two photographic plates, one without the sun and then one during the eclipse, and looked at the positions of stars that were near the sun, and they saw that they were slightly moved in their apparent position. That's because the rays that were coming like this all of a sudden got focused. And so you see that instead of the star being here, it looks like, because the rays have been focused, it looks like it's over here. And so so we know mass focuses light. And what's happening as you collect more and more mass is the light rays get focused more and more, until what happens when matter disappears behind an event horizon is that even the light rays that are, not just passing by, but actually trying to escape, to infinity from the object, those actually get bent around and focused back into the object. So the reason no light, so a black hole is a place in space where no light can escape, where any light ray you try to send out gets turned around and refocused into the black hole. Yeah. And once you say that, you say, well, physics is causal. So if I have something happening here, then I can predict, what can happen later. Well, what can happen later is dictated by how this region in space communicates with other regions of space. And so, if all the light rays are being focused back in, towards the object, then the future, in some sense, is all there, right? So in other words, the future is, where things can get to at some later time, right? But if light rays are getting focused, then in some finite amount of time, all those light rays will come together with the mass that emitted those light rays, will all come crashing down in one place, and that's the singularity.
Yes.
So the idea is that once things fall inside this event horizon, which is sort of like the last surface beyond which, outside the last surface before which you can send a signal out to infinity, to a distant observer.
Yes.
So that sort of last gasp surface is the surface beyond which anything that falls inside that inevitably falls into the singularity. So their future is going closer to the singularity, inevitably. And
Right.
so the singularity is kind of the future of anything that falls inside the black hole. So that's why you would say, I think most people would say that the singularity is sort of an instant in time, where
Yes.
anything that falls inside the black hole hits it at some instant in time.
So we have this information paradox. There's a lot that went on with this idea, but the way I understand this, Emil, is that we say information cannot be destroyed. For mass and energy conservation, it's sort of very intuitive. Information less so.
Yes.
We had a president who appears to destroy information on a daily basis just a few months ago. So why do we say information?
Fundamental physics says you can't destroy information, but you can lose it.
So what do we mean by information cannot be destroyed? But what is sort of the intuition behind it?
Right. So this again goes back to quantum mechanics, and so in quantum mechanics, so the first question we should ask is, what do we mean by information?
Yeah.
Okay. How do we characterize information as a quantitative construct? And so in the sort of 1940s, 1950s, just as computers were getting started, people started to ask this sort of question, asking as a physicist, what do I mean by information? Yeah. And if you think about a data storage device, okay, you ask how much information can I put in my data storage device? Okay, it's got so many megabytes. Yeah. Well, so what does that mean in practice? It means that there's a transistor that's holding a bit of information, okay, but depending on whether if there's a 1 or a 0 in that storage location, and so the measure of sort of the information storage capacity is the number of different states that those bits can be in. So if each bit can be 1 or 0, and I have n bits, then the information storage capacity is 2 to the power n. Those are the number of different data states that my storage device can be in. Okay. So now let's think about that in terms of quantum mechanics. In quantum mechanics, there's sort of two ingredients. There's a space of states, and then there's an operator called the Hamiltonian that tells you how those states evolve in time. So once again, there's this idea of what's the state of the system, and then what's the dynamical equation that tells you how it evolves. So once again, quantum mechanics has that structure. Okay, and so sort of the state space in quantum mechanics then is this what's called Hilbert space, that is how many states the system can be in. And so if your device is not a classical computer but a quantum computer, the bits are now called qubits for quantum. And so there's the notion of quantum information, which is how many quantum states can the system be in. And associated to this is a notion called entropy. And once again, we have a closed entropy means, this sort of means or chaos or whatever. Again, entropy has a very precise meaning as the logarithm of the number of states. So if a state space has 2 to the power n different states that it could be in, the entropy of the system is n times the logarithm of 2, so of order n. And so in a quantum mechanical system, you can't create or destroy information because the Hilbert space, once you declare what the state space is, it never changes. And all that happens is you shuffle the qubits around using the Hamiltonian to evolve the system from an initial state to some future state. So, and you think of in quantum computing, you think of exactly that. You start with some initial state, you evolve to some final state, and you read off the state to determine what the computation was. Well, maybe I should stop and because you have questions.
So from my own understanding, Emil, so the way to think about it is that given some initial conditions, I could determine what the state would be in a future time, given those conditions. And hence, yes. If I start at time equal to 0, I can then know till time equal to infinity what the state of the system is going to be. And hence, that's right. That information is always there. That cannot be destroyed. Is that the way to think about it?
That's the way to think about it. So now if we say a black hole is some quantum mechanical object, then okay, there's some entropy of the black hole, which is how many different states the black hole has available to it. And okay, if something happens to the black hole, like you throw something more in, its mass increases. It turns out, for reasons we'll talk about in a minute, that its entropy increases. So the bigger the black hole, the more potential states it can be in. Yeah. And it turns out also quantum mechanically that black holes can evaporate, which is the source of this so-called information paradox, where you let the black hole go long enough, it radiates away its energy, and it just becomes a bunch of photons and gravitons, in far regions of space. So you can say, where was the information, where did the information in the black hole go? Well, it's now sort of extremely diffusely dispersed in the state of the radiation that the black hole evolved into. And in that respect, you could ask, how is that different from burning a lump of coal? Right? If I burn a lump of coal and the coal is gone, then the state of the coal turned into the state of all the hot photons that the coal emitted. And so in that sense, again, the state, the information is not destroyed, it's just scrambled in some very complicated way that's hard in any practical way to recover.
So what was the paradox then? I know, so the radiation, Hawking came along and said, black holes will emit radiation and over time they will completely evaporate away. And so the stuff that fell into it, all the information that fell into it at some point is going to be all radiated away. But like you say, isn't that very akin to a piece of coal burning and just going away?
Yeah, so the difficulty is the process by which Hawking's calculation works. So let's go back to the time when Hawking was first proposing this idea of black holes as radiating, and actually go back a few years earlier, about the time the standard model of particle physics was being developed. People were starting to think about quantum gravitational physicists, not thinking about particle physics. We're just asking questions about the nature of black holes. And one of the things they noted was a certain analogy between what's called the second law of thermodynamics and the properties of black holes. And what does the second law of thermodynamics say? It says that if you have some system like, I don't know, a glass of water and you stir it, then the energy you put into stirring it very quickly gets turned into heat that warms up the glass of water a little bit. And you lose track of the information about the eddies in the water and so on. It sort of just gets diffused and you lose track of it. And so the entropy of the water goes up. And so there's back in the 19th century when people were thinking about processes like this, involving gases and liquids and so on, they developed the laws of thermodynamics. And one of the laws of thermodynamics is sort of any process you could imagine, any reasonable process, ends up increasing the entropy of the world. So this is the so-called second law of thermodynamics. And so when people were thinking about black holes, they noted that, well, if you throw something at a black hole, it gets lost behind the event horizon and you never get it back. And in the process, the black hole gets a little bigger because it's more massive. And so you could ask, okay, is there something akin to an entropy? Sort of, if the black hole by any reasonable process is always growing, that sounds like the increase of entropy. So is there something associated to the black hole you would call an entropy? And so what Jacob Bekenstein and Stephen Hawking proposed in the early 1970s was that the thing that plays the role of the entropy is the area of the black hole event horizon, this surface of no return. That's the thing that's always growing if you increase the mass. Yeah. Okay, so the first thing that was discovered was that black holes have an entropy, just by thinking about thermodynamics. And of course, thermodynamics is a branch of physics that has to do with, okay, I stir something and this quantity called entropy increases. If I don't know about molecules, I don't know what the microscopic states are of the water after I've stirred it. All I know is that, well, this macroscopic stirring motion got sort of spread out and diffused among all the molecules of the water in some complicated way. So it's like losing track of the precise microscopic state. And so the entropy so black hole thermodynamics is like that. It's saying there's a law of black hole thermodynamics, but the actual microscopics of what's going on sort of under the hood microscopically, if the entropy is telling me, like it should in quantum mechanics, what are the number of different microscopic states that the black hole can be in? Einstein's theory doesn't tell you about that. It just says there's this quantity, the area of the black hole, and there's an entropy associated with it. And we don't know where it comes from microscopically. It's just that Einstein plus Bekenstein and Hawking predict that a black hole has that many states. Okay. So then the reasoning was, okay, if a black hole has an entropy, it should have a temperature, because temperature is also part of thermodynamics. And temperature and entropy are sort of related in the theory of thermodynamics. And in fact, there's a first law of thermodynamics. If the black hole has a temperature and you increase its mass by a certain amount, then the first law of thermodynamics tells you that the entropy changes in proportion. So the entropy and the mass are related in that way. And so if you say, okay, thermodynamics holds for black holes, then the black hole should have a temperature. But what is this temperature? You're telling me the black hole has a temperature. That means it's radiating stuff, and so how could it be radiating? Because didn't Einstein tell us that everything just falls into a black hole and never returns? So how can stuff be coming out of it?
Yeah.
And so Hawking thought about that for a few years, and then in the mid 70s he came out with this really stunning paper that said, yes, black holes do have a temperature, and here's how it works. That if I think about any quantum field, photons, gravitons, scalar particles, whatever, and look at how they behave near the event horizon, then, in quantum field theory, there are all kinds of fluctuations of the vacuum and all kinds of quantum stuff going on. And every once in a while, there will be a fluctuation where a particle-antiparticle pair gets created. And ordinarily, that costs some energy. It costs you energy of the mass of the particles. And by the uncertainty principle, that can only last for so long before the pairs have to reannihilate to go back to the vacuum. But what's going on is that sort of space is kind of stretching near the vicinity of the event horizon. And so what can happen is the particles, once they're created, kind of get stretched apart by the evolution of space-time. And one member of the pair can get out to infinity, that's the Hawking radiation, and then the other member falls into the black hole. And so that's Hawking's calculation, the process by which, it's called the Hawking process by which black holes radiate. And so now the question comes, how is that consistent with quantum mechanics? Okay, and information, the non-destructibility of information, because the pairs that are getting created near the event horizon in the Hawking process are in a unique state. Being in a unique state, they carry no information. Okay. So here's the paradox. This member of the black hole gets out to infinity via a process that carries no information. But if the energy of the Hawking quantum, because energy is conserved, if the Hawking quantum got out to infinity with some energy related to the black hole temperature, then the black hole left behind has a slightly smaller energy, so a slightly smaller mass. But mass and information capacity are related. So the information capacity of the black hole decreased by a process which by itself carried no information away to infinity. So you can only go for so long without running into a contradiction that energy is being radiated, but no information is coming along with it. And so at some point, what's left behind is incompatible with the laws of black hole thermodynamics. So at this point, you have kind of two choices. You say either Einstein is right and Heisenberg is wrong, i.e., black holes are inconsistent with quantum mechanics and the indestructibility of information in quantum mechanics is violated by black holes. And the other option to you is that no, something is there's some subtlety that's not apparent in Hawking's calculation, but eventually when we understand the theory of quantum gravity in sufficient detail, we'll find that it's a quantum mechanical theory like any other, and information is not destroyed. But then something is fishy with Einstein's theory. And so most string theorists, if you ask them, will go the second route and say, yeah, quantum mechanics is fine, but something has to supersede Einstein's theory. And we think we know what that is, namely string theory.
Yeah, so from my own understanding, Emil, so going back to the lump of coal burning, when the heat escapes, that heat has information. So there is nothing inconsistent there. Coal disappears, right. Heat and information escape, everything works out. In the case of the black hole, heat escapes, but not information.
According to Hawking, yes.
According to Hawking, and yes. so that is the issue. Now, so you said either theory of relativity or quantum mechanics. One of those things have to give, and yes. And string theorists believe it's Einstein who has to moderate. Right. But I understand that there are other ideas, right, to sort of explain this in some way.
So to give you an idea of how radical the problem is and why we think it requires a radical solution rather than just a tweak of Einstein's theory, because string theory is really a radical departure, extra dimensions, strings, brains, it's on the face of it, you would say, who would invent that and why? But the reason it's so remember I was saying that the event horizon is this kind of causal barrier that light can't get out. So that's the reason why you think information shouldn't be able to get out. It's that the way we communicate information from one place to another is by sending light signals, right? And information can't travel faster than the speed of light. Because nothing can travel faster than the speed of light. So how could you convey information faster than the speed of light? Okay, and so the information about what formed the black hole is sitting there down at the singularity in the core of the black hole. And there's this causal barrier, the event horizon, which says you can't communicate information about the internal structure of the black hole to the outside, because in between the inside and the outside is this, surface, which is the surface of the fastest light can travel. It's just like the outgoing light rays are barely able to not fall back into the black hole when they're at the event horizon, and anything inside that is swept in. And so this process, the reason this Hawking process doesn't convey information is that it's some random process that's going on at the event horizon, which is completely uncorrelated from the structure of what formed the black hole. Okay, any black hole formed in any way you like has the same Hawking process, conveying the same no information in the radiation. And the reason that's different from the lump of coal is when you emit a photon from a lump of coal during the burning process, you change the state of the lump of coal in a predictable way, right? There's some atomic transition, some excited state of the atoms in the coal, emits some photon, becomes some other atomic state. We understand that perfectly well, and it's just some chemistry. And so the lump of coal left behind is subtly different after having emitted the photon. And so the state of the photon is correlated in a predictable way with the remaining state of the lump of coal. And if you then gathered all of the photons and all of their subtle correlations at the end of the process, you could, if you had a big enough computer, reconstruct the state of the lump of coal in principle using the laws of physics. Okay, but because there's this causal barrier between the inside of the black hole and the outside, general relativity and quantum field theory, as we understand it, has no mechanism by which to communicate that information about the state of the Hawking photon and changing the state of the black hole left behind. And it's not some microphysics. It's not like we don't understand physics at the scale of a TeV or the Planck scale or anything like that. It's the scale of the event horizon of the black hole. And if we think about the black hole at the center of our galaxy, it's enormous. Its radius is, millions of kilometers. Black hole the size of the sun would be about a kilometer, okay? And roughly speaking, the radius and the mass are proportional. So if we say the black hole in the center of our galaxy is, 1,000,000 times the mass of the sun, maybe 4 million, it's like 1,000,000 kilometers in size. And the scale of the problem is occurring at the size of the event horizon, not at some Planck scale. So that's why we think there's some really radical departure of physics that has to happen to explain the black hole information problem. Now, there are other people who, are thinking about other theories of quantum gravity, and the theories that they're propounding have to face up to this issue. They have to do something rather dramatic at the scale of the black hole event horizon. So just twiddling with Einstein's theory and tinkering with the structure of it near the scale of the Planck scale is not going to fix this problem, because the problem can be at scales arbitrarily bigger than that the bigger you make the black hole.
It's a real system. So one idea, Emil, if I understand this, is that if information is encoded on the surface itself, so when that radiation leaves, perhaps it can take the information away with it. Something along those lines.
That's right. So So one thing we could ask is go back to this notion of the entropy being a count of the number of states. Okay, yeah. So there are two issues here. One is this information problem. How does the information get out? What do we have to do to Einstein's theory, or whatever supersedes it, in order to explain this information problem? There's actually a sort of a more primitive problem than that, which is that in Einstein's theory, we just take gravity in 3 space and 1 time dimension, and we construct a black hole solution. They're just theorems in general relativity that says that solution is unique. There is one, if I specify a black hole and I tell you what its mass and its electric charge and its angular momentum are, there's a unique solution of Einstein's equation with those 3 properties, okay? So if the state of the black hole is unique, then how can it have any entropy, right? Because as we said, the black hole was the number of different states that the black hole could be in microscopically. Einstein's theory doesn't have any room in it for different black hole solutions. So before we start answering questions about how black holes, take their information out of them and convey them back into the world, we should ask, how do black holes store information to begin with? What is the microphysics underlying the thermodynamics of black hole entropy? And this is sort of like the analogous question, if we again go back to 19th century physics. People developed thermodynamics as a sort of a black art. And then they ask, okay, what's the microscopic physics underlying the thermodynamics? And they developed, Boltzmann and Maxwell and others developed the theory of what was called statistical physics, that there were some underlying constituents. I mean, atoms weren't discovered until decades later. But if you postulated the existence of atoms, and atoms were in some kind of gas running around, then the number of different states, of the microscopic states of the gas, could be an explanation of thermodynamic entropy. And so the idea in string theory is that, Einstein's theory is, it's got the thermodynamics covered. All we need is the Einstein equations, and we can predict the thermodynamics of black holes. But what Einstein doesn't tell you is what's the analog of statistical physics. What are the microscopics that explain black hole entropy as number of different states? And so a huge advance came out of string theory in the mid-90s, the calculation of Andrew Strominger and Kumran Vafa, who are both now at Harvard, where they looked at black holes in string theory and said, well, what does string theory have in it that we could make a black hole out of? Well, they're the strings. But then by this time, we'd also discovered that strings weren't the only things that there are in string theory. There are other exotic objects called branes, D branes, membranes, five branes. So there's this whole exotic zoology of different branes in string theory, extended objects of different dimensions. And remember, I said that one of the ways string theory accommodates the standard model is by having topology in the extra dimensions. And one of the uses of that is that topology protects the light masses of the particles in the standard model. The other thing you can do with that topology is you can wrap branes around it, right? If I have a pencil, right, I can wrap a rubber band around it. I can wrap a rubber band around it once, or I can double it over and wrap it twice, or I can wrap it 3 times, 4 times, as many times as you like. Yeah. The more I wrap it, the more I have to stretch the rubber band. But remember, stretching energy, according to Einstein, energy is mass. So the more I wind it, the more massive an object I'm making. Okay. And so if you start saying, okay, how many different ways can I wrap these different exotic objects around these topological pieces in the extra dimensions? And you start counting mathematically the number of bound states you make. Then in very special situations where there's enough symmetry, you can do that counting down to the last factor of 2 in pi. And this was the calculation that Strominger and Vafa did. The first microphysical explanation of black hole entropy by just simply counting the number of different ways of arranging the branes in string theory and binding them together.
On the surface,
so we now, those of us in the string theory community are making computations of this sort, and always with perfect. Black hole entropy comes out of the dynamics of the extended objects of string theory, and that's the microphysical explanation.
Yeah, so the extended objects, Emil, so when you say the number of ways you can wrap things around, are we talking about wrapping things around on the surface? Or does
yeah, so here's where, yeah, well, so, so here's where indeed our classical brains have a little bit of trouble with the intuition. So, we usually think about surfaces being in something, like a surface being in 3-dimensional space. And so that's sometimes called extrinsic geometry, the way an object is embedded in a bigger space. What Einstein's theory is about is what you might call intrinsic geometry. that is the geometry of something in and of itself without embedding it in some bigger thing. So when I said I had a pencil and I could wrap a rubber band around a pencil, I had the idea that there was this third dimension that the surface of the pencil was embedded in. Okay, so imagine the surface of the pencil without the third dimension. So what is that? That's just a circle. Okay, so if the extra dimension of space is a circle, then I can wrap a string around that circle once, twice, 3 times, etc. There's no third dimension which corresponds to going away from the circle. That's just what space is. It's just the circle. And string theory has, 6 or 7 of those extra dimensions, and they can have little topological knots in them or bubbles that can be various dimensions. They can be circles, they can be spheres, various higher dimensional things. And each different animal in the zoology of string theory can wrap that topology in different ways and can bind to other bits of brain in different ways. And what explains the black hole entropy is basically the number of different bound states grows exponentially with the mass in a way which appears to be compatible with the thermodynamics predicted by Bekenstein and Hawking.
So if I understand this correctly, Emil, so Einstein says a black hole is a fairly simple thing. There are 3 parameters: mass,
and its features,
charge, and momentum. It doesn't matter if you jumped into it or somebody else jumped into it, it's going to look exactly the same. Yes. And you can sense a black hole's presence in terms of gravity, in terms of electric charge, in terms of momentum. And he stops there, basically, right?
Yes. Yes.
But because of the information issue, because of all the stuff that went into it, there has to be something somewhere that stores all that information, and that is really what you're trying to figure out, right, from a string theory perspective.
Yes, that's right. And if I may, so I just described to you that there was this great success in counting the entropy of black holes in terms of the number of ways strings and brains can bind together. There's a bit of a sleight of hand in that calculation, which I should describe, which is that in order to control the calculation, what Strominger and Waffe did was they worked in a regime where the interaction strength of the strings and brains is small, so that they could actually enumerate the bound states. It's using this an approximation scheme where you're expanding in the strength of the interaction of the different constituents. So like thinking about a gas of weakly coupled constituents. But a black hole is not a weakly coupled thing. Gravity is getting strong. So the way the calculation worked was they say, we know how to do the computation when the brains and so on are weakly interacting. And then if we just extrapolate the result to the regime where the interactions are strong, we know that the brain's bound state becomes a black hole. Knowing for a constituent, the number of different microstates doesn't change. And so you sort of do the computation in one regime where the mathematics is under control, and then you extrapolate it to the black hole regime where it's less clear what's going on because the interactions are strong. But you sort of know a priori that your counting you did isn't going to change. Okay. And so the big question is that this process of tuning the interaction strength between weak and strong, basically what's happening is that, remember I said we were talking earlier about the different scales in the problem. There was sort of like the string scale and the scale of the extra dimensions, the Planck scale, and so on. Well, what's happening in the weak coupling is basically what wants to be the size of the black hole event horizon is smaller than the string scale. That's the reason you can do the counting in weak coupling. It's sort of like the effects of the event horizon are just swamped by the effects of strings and string fuzziness. And in strong coupling, what happens is the size of the event horizon starts to sort of puff up and becomes bigger than the size you naively think the bound state was. And here's where the paradox starts coming in again. Everything we know about in conventional physics says anything in conventional physics in the vicinity of the event horizon, its future is to fall into the singularity. And so all of this beautiful structure of brane bound states, the question is, where does it go when you puff out the black hole horizon and make it bigger than stringy fuzziness? And so, so here's where opinions differ. Some people say our picture of the low energy horizon is still the same. We can trust Einstein's theory, and physics near the event horizon is not so different. But then you have to invoke some kind of non-locality, which communicates the structure of the core where the bound state is sitting to, the Hawking photons that are leaking outside. So either physics has to be sort of non-local on the scale of the event horizon. That's one idea. Another idea is sometimes called the fuzzball idea, which is that once the black hole event horizon starts becoming bigger than stringy fuzziness, the size of the string bound state sort of tracks it. That as you crank up the coupling, the sort of size of the bound state doesn't stay some fixed thing and the event horizon's sort of growing bigger and bigger outside it. That actually, as you crank up the coupling, also the size of the string fuzziness grows in proportion. And so that once you would reach the size of the event horizon of the black hole really would be like a lump of coal. It would be just a lump of coal made up out of these strings and branes and other exotic objects of string theory. And that they're sort of, to the extent that there's an interior, it's some exotic matter of the sort that we've never seen before, made up of these exotic objects. And so this is where I said the black hole is sort of like the ultimate, particle accelerator. We can't make these exotic objects in the lab because we don't have enough energy in the particle accelerators, and we'll very likely never have enough energy. But nature is doing the job for us in the cores of black holes. And the only question is this the detritus of those collisions sort of stay near the singularity and only communicate by some exotic non-local processes to the Hawking radiation? Or does, in fact, the sort of size of the bound state, once you collide the things and make it, does that size of the bound state track the size of the black hole so that the black hole is just some new phase of matter that's itself the size of the black hole and filling the interior?
So one thing I struggle with, Emil, if you say the black hole is a discontinuity in time, does it really have to have an interior? I mean, couldn't we have a situation where there is no space? It is really a singularity in time.
Yes. So, so before I pass on to that, notice something I slipped in, maybe without people noticing, that the first sort of successful calculation of black hole entropy from some microscopic description, down to the last factor of 2 in pi, needed in an intrinsic way the fact that there were extra dimensions of space. I needed the extra dimensions of space to wrap the branes around, to make the structure on which the scaffolding, if you like, on which the black hole entropy could be explained. So one important sort of lesson from string theory, if it's right, is that really, even to understand ordinary things that we know are there out in the world, like black holes, their explanation in string theory makes extensive use of the properties of the extra dimensions. So that's one thing. Now, then you could say that you could ask, well, is that scaffolding sort of immutable and I'm just hanging branes on top of it? Or does the scaffolding itself respond to the fact that I'm draping all this stuff on it? And if I drape enough branes on it, does the scaffolding collapse? And so that's the idea that actually maybe if I drape enough branes around this topology, maybe the topology itself collapses down to 0 size and goes away. And so this would be a scenario where, in fact, space just ends at the event horizon because the extra dimensions sort of pinch off to 0 size and there's nothing inside. So there's a sort of evocative picture people draws. Remember, we were talking about a pencil, and wrapping, strings around the pencil. Well, imagine the tension of the rubber band was so strong that it just constricted the pencil and just made it squeeze off. So, right, so that's what happens at the eraser, right? The pencil just ends. And so, could the structure of the topology of space be such that, way away from the black hole, you have these extra dimensions and there's some fixed size, but due to the fact that you're wrapping the brains around them, as you get closer and closer to the black hole, the tension of the brain starts squeezing those extra dimensions and sort of squeezing the life out of them, so that by the time you get to the event horizon, they just pinch off completely, like the end of the pencil. And there's nothing beyond, because I was saying that the geometry is intrinsic, there's sort of like nothing it's embedded in. The geometry just ends in some kind of cap. And there's nothing beyond the cap. So it's sort of like the process of going in just ends because space ends. And so that's another scenario. But still, it would be the case that you would think that the brains and stuff that the black holes are made out of then would be sort of still sitting there, stuck by gravitational attraction to being, at the bottom, at this cap. And so you would have some sort of structure of brains kind of coating the event horizon, but then with nothing inside. That's one possibility. Another possibility is that there's just some new phase of matter, and there's things to be said for both points of view. And in fact, one thing that's become interesting over the last couple of decades is what happened already starting in the mid 80s, because string theory was new mathematics, was an increasing interaction between mathematicians and string theorists. We both, string theory was developing new mathematics. There was no doubt about that already from 35 years ago. And so then that meant that mathematicians could learn new things by talking to string theorists, and that started happening. And new branches of mathematics have come from string theory, and the things that mathematicians have learned have fed back into forming our intuitions about how to characterize the theory. That's now also happening with condensed matter physics, because we've been talking for the last few minutes about entropy, statistical mechanics of gases of brains and so on, different states of brain, deep brain string matter. So clearly there's something which maybe we can learn from condensed matter physics and the physics of materials, which deals precisely with what are the exotic states that matter can be in. And it turns out in the theory of high temperature superconductivity and other exotic states of matter that condensed matter physicists have been exploring for a long time for completely different reasons, involve very quantum mechanical states of matter that people never saw before, and that have some affinity with the exotic states of matter that we're invoking in string theory to explain black hole physics. So there's a kind of a rich interplay now also between two branches within physics that have things to say to each other as a consequence of string theory.
I know that the Event Horizon telescope had some interesting data. Andrea Getz had the Milky Way's black hole sort of at least experimentally shown. It seems to me, Emil, that black holes appear to be the experimental laboratory for string theory, right? If there is going to be anything testable, that's possibly there, right, somehow.
Yeah, unless there's, I mean, there are a few places, where one still has some vestiges of hope. One is black hole physics. So there's a question of, okay, if black holes are explained by this novel exotic state of matter, be it inside the event horizon or just coating the event horizon with nothing inside, whatever it is, does that structure poke out of the event horizon a little bit? And if it does poke out of the event horizon, how far? If it pokes enough out of the event horizon, then you should be able to detect it by scattering things, by looking, near the event horizon with things like the Event Horizon Telescope. Are there things that you see there that aren't predicted by general relativity, that might be, harbingers of some exotic matter closer into the event horizon? So that's one place we could look. There's also early universe cosmology. As I was saying earlier, the fact that the interior of the black hole, the singularity, is sort of a place where time ends, is sort of like the time reverse of the Big Bang, where time begins.
Yeah.
And so you could ask, in the hot Big Bang, where again you have high energies available to you, the current theory of inflationary cosmology doesn't quite get you all the way up to the Planck scale. It gets you up to the scale of inflation. But again, that's of order the unification scales we were talking about. And so after inflation ends, the universe kind of reheats. And then there's a long period of cooling off. And that's sort of, the last vestiges we see that are the cosmic microwave background radiation. So are there structures that we see either in the microwave radiation, or, if there were strings that were stable and didn't decay after the Big Bang, are they sort of stretched across the universe and we could see their signals gravitationally? So people do searches for gravitational radiation from things like cosmic strings that would be relics, possible relics of the Big Bang. And so those are sort of the two of the places where one might hope to see experimental signatures. But it's not guaranteed. There could be no stringy relics of the Big Bang, and the structure of whatever explains black hole entropy could be so close to the horizon that the Event Horizon Telescope doesn't resolve it. And then we'd be back to square one, doing thought experiments and just trying to reason abstractly about what the theory is.
Yeah, I have a nagging feeling that, again, God is too clever, it's hiding lot of data in small steps, that makes it interesting for physicists for a long time, I think. So you have done a lot of work in this area, Emil. So where do you stand on what's the sort of your gut feel? If you look 10, 15 years into the future, the mathematics of string theory appears really elegant. If it were true, it would have solved a lot of the questions around quantum gravity and other things. But experimental verification appears really difficult. What is your sort of gut feel 10, 15 years looking into the future? Where do you think string theory will be?
Yeah, that depends on what day you ask, how optimistic I am. So I think people will continue to make steady progress so of course, scientific revolution can happen at any time, and they're hard to predict. It's been a while since the last one. The last one was about 25 years ago with, I think when we discovered these other extended objects and made the connections to black hole physics. So, barring that sort of, earthquake in the subject, what I, is likely is a continuing elaboration of the things that we, consolidation of the last revolution, if you like, that we still haven't nailed the black hole information problem. I could see that in 10 to 15 years' time, if I were a betting man, I would say we would have solved the information problem by then.
Yeah. And that's a big deal.
That would be a big deal. That would be saying that a fundamental puzzle about the consistency of quantum mechanics and gravitation theory can be resolved within a consistent theoretical framework. So even without having some experimental verification, just saying that the laws of quantum mechanics and the laws of gravity are consistent with one another would be a huge advance. And you know, and that that I think would go a long way towards saying that, well, okay, maybe we don't understand which particular solution of the theory we live in, but that the theory is right, or you know, that you know, that well, so you could always say, okay, maybe there's some other explanation of black hole entropy and so on and so forth, but I think the only, well, personal prejudice here, my sense is the only avenue that's actually making concrete progress is string theory towards the paradox. And it has to do with what I was saying earlier, that all the other approaches to quantum gravity are just doing little tinkerings around the Planck scale. And that's not going to solve the black hole information problem. Because the problem exists at an arbitrarily large scale, you know, as you make the black hole arbitrarily big.
If we get,
you know, then there are other things that are
computing.
Yeah, sorry.
Sorry. So if we get practical quantum computing, do you think simulation, modeling, those types of things might give us additional insights?
Yeah, I think so. So if we look forward to a future, and I don't know when quantum computing will you know, reach the scale it needs to be scalable. You know, right now we're talking constructing a few qubits in the lab, and you know, controlling them for a few, you know, microseconds. Maybe it's longer by now, but you know, on that scale, you know, if we had a quantum computer which had quantum error correction and you know, was truly scalable, then we could start to imagine doing experiments where we build you know, we build quantum, we build a Hamiltonian to stick into our quantum computer that simulates the collapse of a black hole and the subsequent Hawking radiation. And you know, we you know, show that, you know, we would have to develop diagnostics that tell us an event horizon forms in some approximate sense, and then, you know, the black hole evaporates and so on. But yeah, I can imagine us knowing enough to concoct some model which, in its most important aspects, simulates the process of black hole formation and evaporation in a quantum computer. And you know, that would be great as well if we could manage it.
Excellent. Yeah, a lot of exciting stuff. People getting into this area, I think, will have great time next 30, 40 years, I would think.
Yes, I should say that, you know, because this issue of the black hole information problem does touch on the quantum information theory, another area that you know, we're having fun exploring is the connections, indeed, with the people who come at quantum information theory from the side of quantum computing. And advances in quantum computing inform our understanding of how to think about the black hole information problem. And indeed, one of the things that's come out of string theory is in the quantum systems that have quantum gravity in them, there's a sense in which, you know, structures in quantum information theory, like properties of quantum entanglement of qubits, get, again, geometrized in string theory. And so then again, there becomes a rich interplay between notions in geometry and notions in quantum information theory, which is in fact one of the sort of subroutes, subfields that is undergoing the most fervent development as we speak.
Excellent. Yeah, this has been great, Emil. Thanks so much for spending time with me.
My pleasure. It's been fun.